Yes, yes.
So let's start.
Okay, there is just one thing that I wanted to. So today I'm telling about. So last time we did with small disorder, okay, much smaller than we said. We were not an lattice last time. We were in the continuum. So the weak disorder in the continuum means that the mean free path between collisions it's way larger than the de Broglie wavelength of the particle. Okay? So in this case, what we found is that the probability distribution of finding a particle at x, starting from x0 and Fourier transform frequency omega was one of the density of state at the energy E of the packet. Okay? And then we have to do this thing, right? The average of the retarded propagator x0 energy E times the advanced propagator x0 and energy E minus omega. And then we have to average this over disorder. So I'm not going to talk about this anymore today. And this is true for every localized, non-localized, everything. Okay, this is just we saw. It's just you take a Schelling equation, you create a wave packet, and then you let it evolve with the Hamiltonian, do the Fourier transform, and you get this thing here. Okay, good. From this, we found that if we only consider a subset of diagrams, which were ladder diagrams, which we call diffusion diagrams, we get the diffusion coefficient. We got the diffusion coefficient T. We got also one of the results was that this approximation means that the participation ratio of a wave function of an eigenstate, it's 1 over V, okay? Although, as I said, we expect 3 over V for GOE, okay? But this approximation gives us this. And one thing that I didn't discuss, but I wanted, because I think it's important, because it brings this entire diagrammatic thing into modern ways. Well, now we have computers, we do diagonalizations on systems on a lattice, we get participation ratio, we get what they're called K of T, form factors, and so on and so forth. So, for example, you can use this approximation to compute. So, again, the density of state, total density of state, non-local density of state, okay, is 2 pi I trace of G retarded minus trace of G advanced, okay, at energy E. So when I write this as an operator, okay, when I write this is the matrix element. This, at this point it should be clear. Then we want to see the level correlation function. So this is a bit of a continuation of last lecture before we start going in the opposite limit of strong disorder. Okay, strong disorder is this. This thing, rho of E plus omega alpha, rho of E minus omega alpha, minus average of rho squared. Okay? Again, this, you put this thing in, you see again, we have products of G retarded, G advanced. So we're going to have the same class of diagrams that we inspected the last lecture. If you now select the diagrams that give you the diffusion, and this was done in a paper by Boris Altshuler and it's Altshuler, Shklovsky. Schuler, Shklovsky. Experimental theoretical physics. 1986. Okay? That this thing here is the real part of the sum over all the diffusion modes of 1 divided by dq square minus ion square. Okay? If you do the Fourier transform of this thing, this is the k of t that we have seen many times plotted numerically also for many body systems. And if you do the Fourier transform of that thing, you get t sum over q e to the minus dq square. Okay? The t comes because this is a square, so. Very good. Times t, sorry, obviously. And if you plot this function here, then for very large t is linear, and then it curves down. And it starts curving down. If you are in a box, this thing is quantized, right? If you're in a box, then Q is over 2 pi over L, depending on the boundary conditions, time N. And there is always the zero mode, okay? But then there are also the other modes, and this thing starts curving down exactly at the tallest time. Which is L squared divided by D. Okay? So, from the diffusion diagrams, we can get the K of T, okay? And we can get the onset of the linear behavior. We don't get information about what happens here. I mean, not in this approximation. We don't have a Heisenberg term because we were working in the continuum. In the continuum, the Heisenberg time is infinite. Okay? But just to say that the things that we discussed today by doing diagonalizations or other kind of things, people have looked at them before. Okay? They are in the literature of mesoscopic systems, even by very well-known people. And you can do some expansions, some results can be obtained analytically.
So if you include the Cooperons, what you should see before.
The Cooperons
Cooperons are the
fully crossed diagrams, yes. This is a good question. I think you see something before here. After there's nothing. Okay, so not sure because it's not discussed in this paper, which is pretty technical, but it's pretty nice. This is like peak Boris Altschuler calculations, 6 pages of integrals.
Silly question. I understand the name diffusors for obvious reason. The name Cooperons is kind of.
Yeah, it's Cooper pairs.
But how can I see that a cross diagram is okay?
I don't know why people chose that name. I think that's okay. Actually, because if it's fully crossed and these are inverted, if I rotate this, it's not particle part. Yes. Yeah.
Okay. Okay. Thanks.
Particle instead of particle antiparticle. Okay, good. So this is something that I want to say because this is something that okay. Now let's go for something completely different. So we say that the diffusion coefficient goes down, okay, as I increase the disorder. And my semi-classical calculation actually says that this actually should go down like 1 over disorder square, which just comes from Fermi-Golden rule. Sorry, by the way, disclaimer. Maybe I will have to do more than one pause because my throat is still, my voice is still not. Anyway. And this is the point at which the the Broglie wavelength and the mean free path more or less coincide, okay? And Anderson told us that indeed, after this point, the diffusion coefficient can actually go to zero at a critical disorder. This critical disorder depends on a million things. First, it depends on the dimensionality of the system. The second depends on the lattice. Okay? If you are on the lattice, obviously. And it's, as far as I know, there is no way of looking at, of finding this critical disorder or understanding well the transition starting from a small disorder. But that's also not a good idea in general in physics. When you have two phases, right? You have the Ising model, okay? You have a small temperature, you have a magnetized phase, at high temperature, you have a paramagnet. So what you do the low temperature expansion at small temperature and the high temperature expansion at high temperature, okay? If they tell you that the phases are stable, it means there is at least one phase transition inside, okay? It's not so easy to turn a low temperature expansion into high temperature expansion. I mean, they contain the same information, but they're not easily. So, okay. Some systems, for example, they have dualities, like for example, the Ising model in 2 dimensions, which is connected to the fact that the system is integrable, but these are very rare cases, okay? In general, when we want to study phases, what we should do, we should take one expansion here, one expansion here, and see if at least one of the two fades down at a certain point, okay? So, the purpose of today's lecture is to do the large disorder expansion, okay? To do this, it's better to start on a lattice. Okay? On a lattice, and let's take an Hamiltonian, which is a hopping term, T. And I'm not even going to use second quantization, just going to use first quantization. And the disorder is a measure of the variance of this epsilon I. For example, epsilon I are random numbers extracted uniformly from the integral minus WF, WF. At this point, I have a measure of the strength of the disorder, I have a measure of the strength of the hopping, and then this, okay? So, what am I saying? I'm saying that the Hamiltonian, this will be the unperturbed Hamiltonian, and this will be the perturbation. Okay? And then I have to do some kind of perturbation theorem. Good. Now, what we're going to see is that the probability distribution to the amplitude, okay? Now we're going to have our propagator, GE, which is 1 divided by E minus H, which is 1 divided by E minus H 0 minus V, okay? And as we did last time, we're going to expand this in the usual series. Using the usual identity. Okay, so if I iterate this, I keep getting the terms in the series. Good. What I want from this propagator is, okay, it's not what I want. So what will happen, okay, is that the propagator, sorry, G, The propagator, either retarded or advanced, doesn't matter, at a given energy E between points x and x0 will be exponentially small in the distance between the points. Okay. Now, what does this mean? Well, first of all, that we have no transport. Okay? Because once I put something which is exponentially small here, and I put it in here, and I do the Fourier transform, unless something strange happens during the Fourier transform, I get something which is exponentially small. So I put a particle here, I wait a certain time, the probability to find it far away is exponentially small in the distance. Okay? There is no light cone, there is no diffusion, there is just an exponential small probability to get the particle there. The other thing that I get is that it is exponentially small. Let me remind you that the propagator I can introduce a resolution of the identity in terms, write it in terms of eigenstates, okay? Depending whether it's retarded or advanced, in principle, I should add the term here. Okay. Now, if I look at the residue of this propagator at a given energy, which is morally saying that I have created a packet around a certain energy, as and a certain energy in a certain position, then you see that if this is exponentially small, it's because this product is exponentially small. Okay? So if this is exponentially small, okay, then this product for a given energy, okay, is exponentially small. Which doesn't mean, well, which means essentially that either, you know, my particle, my wave function is concentrated around x0, and that's actually typically the case, because if I took the residue around EA, I'm going to get the wave function there. Okay, and I'm looking at the same eigenstate at distance x. Okay, or it could also be, sorry, so this is one, okay, because I just took around the localization center, and this is x here. But it could also be that somehow I excited an eigenstate which is somewhere in between x0 and x, but still I have an exponential tail here, an exponential tail here, and I have this is still exponentially small in the distance. Okay. So exponential localization in the propagator means there are localized eigenstates. Localized eigenstates are associated with participation ratio, which is order 1. Okay? As you can imagine, because if I sum over x psi a of x to the fourth, this is typically just the radius of localization. Where is it here somewhere? This is proportional to the localization length to the dimension d. Okay. But so localized states are associated to absence of level repulsion. And this you should try to understand.
Minus b. Minus b. Because it's inverse of this way. Minus b.
Yeah, this is less than 1, clearly. I mean, it was 1 over v. So it's, yes, exact minus. Thank you very much. Thanks. So, number statistics is, it's not easy to calculate directly the level statistic, but you can, there is a simple argument that says that there shouldn't be any level repulsion. And the argument is the following: suppose that you have two eigenstates, okay? If the radiations in energy, maybe this needs a little pause. If the energies are radiation in energies, they are very far away in distance. Why is this? Think about just this term here. Okay? Our eigenstates are just the lattice sites and the random energies on top. Okay? If I throw them completely random, and I take one and I ask, where is my next one? They were completely random. So it's anywhere in the lattice. There's no correlation by definition. Okay? So the average distance between an eigenstate and its next in energy is system size. Okay? Just because they are uncorrelated. It's not an argument about anything. It's just an argument about taking random numbers. Now, okay, so let's call this epsilon 1 and epsilon 2. Okay. Now, if I make a little change in the energy on epsilon 1, okay, and I ask how much these two are gonna come close to each other, then I have to solve the the 2 by 2 problem, okay, in which I have something like epsilon 1, epsilon 2, and then I have the matrix element. The matrix element of my perturbation, okay, so I change my disorder by an operator delta W, and then I have delta W 1, 2, delta W 1, 2. Okay? So what's delta W 1, 2? It's a matrix element of my disorder of the two eigenstates, psi 2 delta W psi 1. Since this is a local operator, sorry, not delta psi, okay? Since this is a local operator, this thing is going to be again exponentially small.
Like against side occupation.
I'm just changing, for example, the energy here. Okay, this is going to be proportional to the change. So there is delta here, and then e to the minus the distance, and we say the distance is over the L divided by xi. Okay, so what I do, I change the energy epsilon 1 and epsilon 2 to make them cross. I change my disorder. I go to another disorder realization, which is very close by, in which I've taken this site here, and I'm changing slightly the energy on it. It will intersect the energy epsilon 2, because by definition it's the closest one. We choose it to be the closest one, okay? And there will be a level repulsion. What's the value, the minimum value here was this, for this level repulsion? Well, it's exactly the delta W. This delta W is going to be exponentially small. So the minimum gap is going to be exponentially small in the system side. Okay? So in this sense, you can see that exponentially small gaps are going to appear with huge probability. Now, the average gap, instead, it's still the band width, which is, the T, let's say T plus W. Okay, times the number of dimensions. 2 times the number of dimensions plus W. Okay? That's the band, and then divided by L to the D. This is the average gap. Delta is a bad notation. Okay. So the average gap is L to the delta. There are many exponentially small in L gaps. It means that the probability distribution goes all the way to 0. There is no level repulsion. Okay, good.
One curiosity. So, but the typical, it still goes L equal to D to minus D, right? Not exponentially small either. I
Yes.
say there are many, but for the median,
Yes.
it's still 1 over L to the D.
Yes. Yeah. In fact, there is no delta function here. The typical, the median, but there are many of these things, many gaps here.
Sorry, this gap is between the two, F1 and 2.
Yeah, as a function of W.
You change a little bit the disorder. So the thing is the following. Suppose we have one disorder realization, okay? I take one state and I look what's the next, the eigenstate next to me, okay? With very high probability is the state which I call 2, which is localized very far away, okay? Now I say, okay, let me change a little bit the energy of this state here by changing my disorder with an operator delta W. What's the typical gap that I will encounter in this thing? Okay, the typical gap is much smaller than the typical gap over the entire system. Okay, so there are many small gaps. There is no level repulsion.
And the gap with the next level, not the nearest one, the next, let's say the nearest one is smaller in order. How much smaller?
Then what?
From this is from the nearest level, no? But from the second nearest level, for example, it should be smaller than this one, or it's comparable to this order.
You asked the second minimum?
Yeah, the second minimum will be
The second minimum is comparable. I mean, this thing here is typically is of order 1 over V, 1 over L to the D. Okay. So the gaps, this is the typical gaps, okay? The gaps, it's not that this gap is small. The argument is not that this gap is small. The argument is that I can make this gap smaller than the typical gap by changing a little bit the distribution of disorder. Okay? This is the typical, as Lev was saying, this is the typical, the average, whatever. The distribution of the gap is fine. because I just take A to the D random numbers and I throw them down on a line. What's the average distance between them? 1 over L to the D. Okay, so fine. The issue is now I change a little bit the distribution of disorder. There's nothing special in my distribution of disorder, right? Let's change it a little bit. I change it by 1 over L to the D. Do you get gaps which are of this or much smaller? I get gaps which are smaller. So in these average and typical values, there are actually gaps which are much smaller. There is no level repulsion. Okay? If I did the same argument with plane waves, this thing here would have been over there 1 over L to the D. Do the calculation, okay? If instead of taking localized state, you take plane waves, you do the same argument, you see that this goes down, but stays of order 1 over L to the D. So there is, there is nothing less than 1 over L to the D. So this distribution should actually go down.
By plane wave, do you mean localization in Manett's space?
No, I mean I just pretend that even though the distribution is random here, my eigenstates are plane waves.
Yeah, localization in Manett's space. I don't see the difference between this and just you do the Fourier transform. You have this.
Yeah, I say plane waves, you say localized in momentum space. Yeah, they're plane waves.
Yeah, I don't see the point in the sense of small absence of the small gaps in the plane base. Because the Manett's space, they will be localized.
Let me see. If instead of taking localized states here, to calculate this matrix element, I take e to the I k2 dot x divided by square root of v.
If it's the operator block, this.
Yeah, yes. If the operator is local, then you get 1 over v from this thing here, okay? And so you have 1 over v, 1 over v, 1 over v, 1 over v, everything is over 1 over v, you're never going to generate anything smaller. So thank you. This actually allowed me to clarify. Good. So now we have to do perturbation theory. Now, this perturbation theory in the hopping, okay, this is large, this is small, it's called locator expansion. Perturbation theory, T over W on the lattice. T over W is assumed to be a small parameter. Okay, so the first term, let's look. So now we have G0, which is 1 over E minus H0, okay? Now, H0 is diagonal in the lattice basis. So G0 of Yx at energy E is going to be 1 over energy minus epsilon x delta Yx. Okay? The hopping on the lattice instead, okay, V Yx is T if they are minus T, okay, if they are near stable, 0 otherwise. So let me actually.
Do we need more math?
Not yet. I think my problem is that I leave the cap off for too long. So they need to a little bit recuperate humidity. Okay, so now the idea is that I have a lattice Actually, on the blackboard, I have a nice lattice, so I'm going to use this. And I want to compute the propagator to go from this point, say, to this point. Now, this is going to be 0 unless I go to a sufficiently long order in perturbation theory. So in perturbation theory is going to be 0 plus 0 plus 0 plus 0 plus 0 plus something. And once this starts to be non-zero, then I have a lot of other terms. Why? Because this thing just moves me of one lattice side. Okay, so one element in perturbation theory would be a point from the point x0 to the point x. This is the first non-zero term, okay? Let's assume this, what did they call this? This is the distance r, okay? So my propagator to go from x0 to x at energy E, we start with the term which is t to the r. And then I have the product of all these things along the path. Product over all the points I on the path P, okay? Sorry, this contains this term, okay? It's the first non-zero term. Okay. Of 1 divided by energy minus epsilon. Okay?
Minus the
Yeah, this is gonna bounce back and forth. So it's not too important. It's important to get it right, but yes. No, actually no, because the V is minus T, but the series is in minus V, so this is plus. And the geometric series, the correction is there is minus V. Okay, good. And there are the other terms. Now, in principle, I could write this forgetting about issues of convergence, non-convergence. Let's do this, okay? As a sum of all the paths P that go from x0 to x. All the paths, meaning paths that go straight to x. Paths that I have a blue here, yes. Paths that, you know, they were going straight, but then at a certain point they make a loop, then they pass again here, and then they go like that. Okay? Paths that do something like this. And come back, okay? And then they do this. All the possible paths. Now, this formal representation diverges. There is no radius of convergence. As soon as it turns on T, this thing diverges. Fortunately, however, the thing we have to do, we understand this, the divergence of a perturbation theory sometimes means you just done something stupid. Eh? You can mend it and then go on. The first thing that we did is, so this is sum over all the paths, right? The first thing that one can do is recognize something like this, right? If I have a path that does something like this, now forget about the lab. Yeah, maybe now we need another. There's a path that, you know, makes a loop and goes back. This, as you know, is a self-energy correction. Yeah, the results, these are the results. This one was doing, okay, let's see. This is a self-energy correction, okay? So I had my G, it's actually, okay. I have my G and I have my product over all the I's, okay, on the path. And then I can add a correction of self-energy correction depending on the site and on the path. Why on the site? Because I'm summing all the paths that go like this, or, you know, here, here. Why on the path? Because this extra thing here cannot touch the path. Okay, so this thing is already part of the path. So something like this is not, you know, something like this is not allowed. Okay. So these are self-energy corrections.
But it's not allowed. I need to not double count.
Not double
count
yes,
for
yes,
one of the two.
yes, it's exactly. It's not part of the self-energy. It's part of the path.
No, I will say that enter as self-energy for one of the 2 points that are part of the path, and for the other is like, let's say you have one loop.
Yeah, so if this, and then I do this, and
Correct.
this.
So you don't want to, that loop you want to count, but you don't want to insert in 2 self-energies. You want to insert only one of the 2.
Exactly. Exactly. That's what I mean. So you need to remember which path you're doing.
Correct.
Okay.
Correct.
Okay. Now, good. If you compute the self-energies are always going to be of order T squared divided by W. At least. The shortest self-energy thing you can do is to go on up like this. Here, you go here, and then here you get T squared divided by W. Okay? So the worst that can happen is that if these 2 sites are in very good resonance, by chance, but if you go through all the lattice, you're going to find 2 sites we are. Okay. So this problem now becomes like the problem I've solved there. It's a 2-site problem. I diagonalize, and I get an energy which is of order T. Okay. So instead of having the rest, I've split the resonance. If I split the resonance, I've increased the denominator. If I increase the denominator, I've reduced the contribution of the path. So if I forget about these things altogether, okay, then I'm making an error which goes in the right direction. Okay, I want to prove that the series for W sufficiently large converges. And by, oh, thank you very much. This one can go away. I have one with this one. So if I now neglect these things here, what I was saying is that if I neglect this, okay, I set this equal to 0, I'm doing an error in the right direction. I want to prove that the phase is stable. I'm making it less stable. So if I can prove that it's stable, adding this thing, my proof will be even better.
I simply ignore it. Cannot be, because we introduced that, you know, we knew that that was diverging, we introduced that.
Some,
So
yes.
I simply remove, I fuck up again, I go.
No, because I've made less paths now.
Okay, I lost that part.
It's the number of paths, it's the issue of the paths, right? Now, this sums over all the possible paths.
Right.
Now I only sum over non-backtracking parts.
Okay, fine.
Okay? Now this now is turned into sum over non-backtracking parts. Non-backtracking. Okay, of the product over I t divided by E minus epsilon I minus sigma. And if I remove this, I'm making this propagator larger. So if I still prove that it's exponentially decreasing, I'm fine, because the true one will be smaller. Okay? Not repeating, not backtracking. I think we call it non-repeating. Oh, by the way, most of these things you can find first, obviously, in Anderson 58. Okay, and then we wrote a paper with Valentina Ross, Francesca Pietracaprina, my two former students, and myself. 10 years ago, probably. No, not this one that I'm talking about. This is another one. Yeah, forgot the Nobel Prize in the Mr. Authors. No, not this paper. This paper was just on this locator expansion numerically implemented. Okay, what we can do is, okay, now again, these terms here are going to be of order t to the w to the r, to the length of the path, LP, okay? So let's take the shortest paths. They're going to give the largest contribution. Shortest paths from x0 to x. Okay? Right.
Once again,
It's an
it's
approximation.
in the bad, it's in the good direction.
Yes.
For this, even more.
Yes. Okay, good. The shortest paths. Take a lattice. Okay, good. So what are and how many there are? This is important. Okay, let me say this and then we will stop. Okay. So how many there are? Oh, sorry. Okay, this is a nice small, math Olympiads combinatoric problem. No. The shortest paths are from this point to the other, right? I have distance 1, 2, 3, 4, 5, 1, 2, 3. Okay? So I have Manhattan distance 8. How many of these paths there are? Well, I can choose, right? I have to choose 3. In this case, for example, the 3 steps up, want to do the 3 steps up, okay, and the other. So these are 8 factorial divided by 5 factorial times 3 factorial, which is 56. Okay? So, how many there are in general? If you have d-dimensional, you have the multinomial expansion. Okay? And that's the worst case. The case in which there are there is the maximum number given the length. When it's the diagonal, right? You're in the diagonal of a d-dimensional cube. Okay? Then for the diagonal of d-dimensional cube, this, of course, r, yes, the distance r factorial divided by r divided by d factorial to the d. Okay? Now, this is an exercise for you students. Check by using Stirling expansion, okay, approximation, that this is d to the r. Okay? There are many factorials, but in fact, there is only an exponential number of paths from this point to this point. Okay? This is important. Okay, the fact that it's exponential. Let's make a break for 10 minutes.
Sono d'accordo che andando su quelli più corti tu ti metti nella condizione peggiore, nel senso che gli altri, però potresti averne tanti di più, quindi ci potrebbe essere un balance che...
But now we think so we reached our approximation, which we call the forward scattering approximation, in which the sum over the shortest paths p from x0 to x, okay, of the product over all the sides x t of e minus epsilon x. Okay, we know that there is an exponential number of such things. The number of shortest paths grows at most like an exponential, depending on the aspect ratio, okay? The exponential d to the distance r between the points, okay? And so we have a sum of product of random numbers. Okay, how many of these products there are? Exponentially many. Can these random numbers be independent? No, because the independent numbers are the epsilon x. Epsilon x, there are only r to the d of them, okay? We have r to the d independent random numbers, which are generating d to the r random numbers. Now, if r is much larger than d, this is much larger than this. Okay? So we're again in troubles. Okay? So what do? We can do a couple of things. Okay? First thing is we can compute this numerically. Okay? Wait a second. How can we compute something which is a sum over an exponential number of terms numerically, efficiently? In principle, you cannot, right? But in practice, there is a very nice trick, which I'm sure probably it's even before in the literature, but I've learned from a paper by Medina and Kardar. Medina, Kardar, 1993, I think. which works like this. They were studying the so-called sign transition in the Nguyen-Spivak-Shklovsky model, which is a model. It's an interesting story. Okay, so just go and look at this paper. There is a paper by Medina Cardar. There is another paper, but this is a PRB, I think. There is a PRL, which is slightly before, which has more authors. Beran Kardar from MIT, of course. And the trick is the following. Take the adjacency matrix A, okay, of the graph. So I have a graph, I have an adjacency matrix. The graph is L by L by L by L. My adjacency matrix is actually sparse. Very, very efficient, actually, to do. And then write the diagonal matrix, which has 1 divided by E minus epsilon x on the diagonal. Okay? And AXY is the adjacency matrix of the graph. And then we write a vector psi, which has L to the d components. And you initialize it in the 0 where it has only amplitude, let's say this one here. And then what do you do?
The epsilon x, so here you are doing one disorder realization.
Disorder realization, okay? And then you write the transfer matrix T, which is A times D. Okay, this is a sparse matrix because this was sparse and this is diagonal. Okay, and then you apply T. When you apply T over psi, you see that this will move. Actually, if you want to take the adjacency matrix of all that goes all in the positive directions, okay? So half of it, the one that is all increasing the x or y or z coordinate, okay? This way you don't have backtracking. It's more convenient for the numerics because the vector remains sparse itself. So this will move the weight to the neighboring two sides, and so it will be 0 here, will be something here, 0, 0, 0. Okay, then do it again. These two move to this, and this. Okay, and we automatically do the sum. So psi 2 will be T psi 1, and this will be 0, 0, 0, star, 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 0, 0, 0, and so on and so forth. You do this R time.
Something along the diagonal, so I should also keep something on the sides where I am, no?
No, because this is 0 on the diagonal.
But no, but D is not, D is diagonal, no?
But it's always multiplied by A. A doesn't leave anything on the diagonal.
Yeah.
A moves you away from the diagonal. So even if you multiply by the diagonal, then okay? If I do this R times, if I do the transfer matrix and by psi 0, okay, you get something which has 0, 0, 0, 0, 0, 0, and then as the propagator here, G, X, X0, E. So you need to read the last entry of this sparse vector. So you just need to do R times sparse matrix multiplication. Nothing is exponential. This is important because you see, when people look at perturbation theory, in particular in disorder, but also in many body cases, they say, oh, there are n factorial terms, or there are exponentially many terms, certainly will not converge, certainly we do that, certainly we do that. But these are not independent. So if you find a smart way of doing the computation, it will show. Okay? And if it shows, what happens is these things actually have cancellations among themselves. Okay, good. So we did this in this paper with Francesca Ross, Valentina Ross, Francesca Peter Caprina. We did this. You do this for, you generate this thing, you can do, in 3 dimensions, you can do 200 by 200 by 200, okay? And you compute these amplitudes, and then you store them, and you have to look at the distribution, because these are random numbers. So what do we want? When is this thing going to be localized or not? First of all,
Hello, sorry.
Yes.
So sorry, I think I got you last bit here. So the whole point of writing down size is to avoid the summation of over exponential many terms there. So it's just a numerical trick.
it's just a numerical trick. Yes.
And sorry, is it clear why this works, or you're just telling us how to do this? Because I'm not sure if I follow why we should get to propagate our games here.
Okay. So if you look at if you unfold this product here, okay, this T to the R, you do dA, 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 and you unfold it, you will see that you get exactly this thing.
Okay. So more or less just by working out the algebra, we can see that this is true.
Yes.
I see, thanks.
Anyway, just to confirm, suppose that I do a mistake and I go to TR plus 1, I start to see the non-shortest path contributions to the propagator. Am I right? Cioè, the shortest path, the fact that you select is exactly because you are stopping the procedure after.
Actually, if you take the adjacency matrix that moves you forward, the T to the R plus 1 is 0. Because you arrived here and you were pushed out. If you don't do that,
So if I take the full adjacency matrix, I still.
then this vector becomes full,
Right.
and whenever you go and look, it's actually summed all the paths that go back to that thing there.
Okay, yeah.
Numerically, it's convenient to keep this vector sparse because the memory requirement. But if you want to do the calculation that way, you can do that.
Okay. Yeah.
So yeah, it's a very nice trick that allows things. Okay, so first of all, if I take, let's assume that we are in the localized phase, right? Okay, so I want to see stability of the localized phase. So I start from the initial state x0, which is some energy epsilon 0, okay? And if I do E minus epsilon 0 times the propagator x0 E, and then I take the limit E that goes to epsilon 0 here, I isolate the wave function at energy, whatever, let's say the energy epsilon 0, okay? I see the renormalized wave function, the perturbed wave function, which had energy epsilon 0 without T, okay? So it's something like this. Okay, and this is more or less 1 because we are in the localized phase. So if I remove one of the denominators, if I substitute epsilon with epsilon 0, I'm looking at the amplitude of the wave function, which was supposed to be concentrated here, here. Okay? Fine. So then let me define this thing here. Let me define this random variable zeta r, which is 1 divided by 2r logarithm of psi 0 x squared. Okay. This is a random variable that I obtain with this numerical procedure. It has a certain distribution. Since it's the logarithm of something, even though this something here doesn't have any positive momenta, and this I will show actually, because there are denominators fundamentally. So if I take the absolute value square and take the average, I get infinity. But if I take the log, it doesn't matter. Okay? So this thing is a certain probability distribution. Okay? So ZR, E of ZR. Now,
You're saying that that variable per se would be fat tailed and you cure by taking the logarithm.
yes. Okay. So this has some Gaussian distribution, more or less. Okay. We are actually going to dwell into what that distribution is. Now, I can do, now I have to take R that goes to infinity. Okay. When R goes to infinity, these distributions peaks. And now, depending whether it peaks on positive or negative value, z0, z infinity actually, whether z infinity is positive or negative, I have localized or delocalized state. Okay? So, first of all, if this is localized, normally this is exponentially decreasing. I take the log, I get minus r, which is the distance between, divided by xi. This r kills the r, and I get minus 1. Okay? If in practice this thing can actually not be, if I were computing this wave function properly without doing any approximation, the smallest it could be would be 1 over v. Okay, so this would be like log r divided by r, so it would be 0. In practice, because of all the approximation that I'm doing, once this series starts becoming diverging, there is nothing stopping it. Okay, so you're going to get essentially that this number goes from negative to positive. So the first thing you have to do is you have to do this numerics for many system sizes, idealization system size to build this probability distribution, but this is all extremely fast. Okay. So you do that, then you find this thing, and then you plot it as a function of disorder. Okay. As a function of disorder, you find something like this. Okay. And you find that the critical disorder, you find the critical disorder for your system. You can
somehow already the collapse for various system sizes because it's already.
The good thing is that when you increase the system size, this this just shrinks, okay? Example, you don't get something too bad, right? For example, the transition that you get, okay, for d equal 3, so as a function of the dimension, for this Fourier approximation and the true numerical one, okay, it's actually not that bad. In 3 is you get like 27.0 and the true one is 16.55. In 4 dimension you get 41.4 and the true one is 34.62. In 5 dimensions you get 59, I think, something like that, and the true one is 57.3. I mean, it's a good, it's a good approximation for such a dumb, approximation. This is the, if you do an approximation, you just don't find transition.
So to do this numerical calculation, like doing the same effort at doing this the usual transform matrix, right?
Yes.
So if I just don't do any approximation and do the transform matrix calculation, it will be same effort.
No, the approximation is the transfer matrix.
Right, starting from side, taking the full transform matrix and propagate it and get the localization there. The exact.
But that's what I'm doing.
No, here we are. We're making an approximation. Yeah,
Approximation is the self-energies.
it's just a self-energy.
The self-energies.
So, okay. Yeah.
The self-energies push the disorder to much smaller. Yes. And the self-energies, there is no way that you can do it so easily.
So Antonella, from what I can see, the implication is that as you go to larger T, you're getting closer.
Yes.
So can you actually show it's asymptotically exact?
I think you can show asymptotically it reproduces the 4K, the two. We'll see when we talk about the beta lattice. Because you know there is the 2E versus 4. That's the difference. Yeah.
There's only a 2 and 1. It's
And 2-1, you get something, but we know that there is no transition. Actually, that
Don't see that there could be a disorder is here.
no. In fact, Anderson did not realize in its first paper that in 1 dimension things were always localized. To do that, you had to wait Thouless. Thouless showed that in 1 dimension things are always localized, and found a formula that connects the localization line to the density of state. Okay? To go to 2 dimensions, show that 2 dimensions is always localized for the GOEN, for the real symmetric matrices, okay, not sympathetic. You need to wait Anderson and Thouless together. The game of 4. Sorry, not Anderson. Yeah, Richard Dell, Ramakrishnan, Abrams, Anderson, Richard Ramakrishnan, okay. And that's the game of 4. And I will also talk about that. Okay. It's also for many body Hamiltonians. And we did it in the paper with Francesca St. Peter Capina. And if you do that, there is a factor of 2 wrong in the axis of in the label of one of the thing. You find also that there is a transition for the many body, and the transition is around like 4. Disorder for the Heisenberg.
Interesting, because
No. Certainly not.
I think, because we know that in small d this is a bad method.
No,
So
but we just overestimating, so the transition will be even smaller.
Yes.
yeah, that's right.
Yeah. Yeah.
No, but wait, but then you are computing
No,
the
the
paths
thing will be
not
doing in
really.
2D many body. There you expect availability with.
Actually, 2D women are good, actually, because but this it shouldn't be difficult because I mean writing the adjacency matrix of the hypercube in 2D and this thing here. You can go to 50 spins.
You are playing this game in the operator space, so that is a very it's not anymore a 1D result, right? It's a one. I mean, it's now in an abstract space.
Yes.
Okay.
Yeah.
So that's why maybe one can hope to trust because it's highly connected.
Too many uncontrolled approximations here. I mean, this now it's become a game of trusting one numerics against the other. It's, please.
I'm not sure if I understood it correctly, but you could create a transfer matrix that goes back and
Okay.
then reapply the one that goes like forward, and you create one loop, right?
Yeah, in fact, the adjacency matrix of a graph, okay, you can split it in forward, okay, A plus and the rest, okay. Now, depending on how many directions, you can, let's say we are in two dimensions, for example. You always go forward, or you go forward and backward, or you go backward and forward, or you go backward and backward, okay? You split the adjacency matrix of a lattice into adjacency matrix. I can go always forward, so here, or always forward and backwards on one side, okay? So for example, here I go forward in the x direction, but backwards in the y direction. Now, when you do the product, you get all possible things. Okay, so if you just consider this, you go straight to the end. If you leave the other things, you will get, as Dario was saying, you will get all possible paths, also the paths that go back. So if you don't look at just this last thing, you look at the other ones, you're going to get the sum of the amplitudes to go in r steps at a distance r minus 2, for example. So clearly there have been repetitions or longer paths.
Check, you consider all the terms, and you don't took the self check. This should diverge very badly. If you take all the terms, you start to go to very large R because you are not introducing the self energies, but you are taking all the paths, so should diverge very badly.
Probably, yes, yes. Yeah, I haven't.
Okay.
Okay, good. Okay. Now, one thing we should check. We should compute. Okay, there are these amplitudes. Okay, the amplitude associated to a path, AP. Now, the amplitude associated to a path is an interesting random number, which, as I said, does not have an average value. Okay. See if I can do this. So, for the moment, let's forget the fact that in fact the amplitudes of the paths must be correlated, even though the disorders are uncorrelated, because there are way too many paths. Okay? The exponential number of paths. A polynomial number of independent variables, clearly they are correlated. Okay, pigeonhole principle. There is a graph, however, on which this is not true. The graph is the Bethe lattice, or regular random graph. In a regular random graph, there is only one path to go to a given distance. So in order to warm up and compute these things, when I compute this on the beta lattice, let's look at the probability distribution of AP. But let me tell you, so what's the beta lattice? Beta lattice, KD3 or whatever, it's just 3. Okay. Now, my question is, I start from x0 and I go to x. Okay. And clearly there is one single path that goes there. Okay, so there is no sum. However, there is an exponential number of x's at a given distance from x0. Why should I pick just that? Okay, so I should look at the maximum over all the x's of the amplitude of the path that goes from x to x0 square. This will be my indicator of whether I'm transmitting somewhere or not. Now, on the beta lattice, really, on the beta lattice, so if I stop here, okay, this is my graph, nothing more, nothing less. I have not forgotten anything. You never have an ergodic region, a region in which the wave functions are ordered 1 over v. Okay, as long as you put a little bit of disorder, what you get is multifractal. So there is, a different amplitude per every site, and the participation ratios are not 1 over v, but 1 over v to some power, less than 1. Okay. Instead, I close this, okay? I close it in a way that the leaves, they also have connectivity through, like the rest of the tree, and so on and so forth. So imagine to close it. Then this becomes what's called a regular random graph. Regular means that the connectivity is regular. Every site has the same connectivity, 3, 3, 3, 3, 3. There are no leaves, okay? When I do this, you can check the number of paths that leads me to a point here, again becomes exponential. Okay. So what I have to do is I have to take the maximum over an exponential number of objects. Okay, either I look at a tree or I look at a regular random graph, exponential number of things of this random variable here. If this thing, despite the fact that I've taken the maximum, is still exponentially decaying, then I am in the localized region. Okay? I could have done the same thing here on the d-dimensional lattice, but while here they are all independent because there is only one path to go from x to x0, and then I change x, there is only one path, and these are, and if you look at the number of random variables, is exponential as well. On the d-dimensional graph, I couldn't do that. That was not justified. Okay. All right, so let's do that. Okay. Let's take this object here, AP. Let me call it alpha, AP modulo square. Okay. which is t squared divided by, let's say, I already did that limit e that goes to epsilon 0. It doesn't really matter. Let's, and or let's set e equal to 0. Okay. For simplicity, you can do the same calculations for any value of e. Okay. Product over p epsilon p squared. Okay. First of all, let's take the average of alpha. Okay. Let's see. So the average of alpha is, product over p t squared, average of t squared divided by epsilon. Sorry, what epsilon? No, what times? Epsilon x on p. X on p, epsilon x. Okay, so this is the integral in the epsilon divided by w minus w half t squared divided by epsilon x squared. Okay, this is infinity. So there is no average of alpha. So we cannot talk about average values. This is very important in Anderson organization. You never talk about average values. Okay, you talk about typical, median, maximum, everything. Okay, average values tend to have these things. So don't consider the full distribution. Okay, Anderson organization is a game of looking at distributions. Okay, I will compute the probability distribution of a variable which is the product of independent random variables. There are two ways. This is a cheap and dirty way. Take the log. There's another more elegant way, which is take the Melling transform of the probabilities, but becomes the product of the Melling transform. But let's do the following. Let's take the log, okay? Good. So this is t. So we want product over x, 1 over 1 to L, okay? T over epsilon x squared. This is t squared divided w half squared, everything to the L, okay? Product over x of 1 over, I don't know what to call it. This, what did I call it here? No, I didn't call it. Fx squared, okay? Fx now goes between minus 1 and 1. Okay, so this product is always larger than this because these are always less than 1. Okay, so this is always larger or equal than 2t divided by w to the 2l. Very good. Now let's take the log as our friend suggested. Log of p squared will be 2l log 2t divided by w minus sum over x of log of fx. Actually, let me subtract the 2. Yes, you're right. Yes. Actually, let me subtract this and let me call this z, which is log of AP squared minus L log of 2L log of 2T over W, okay, which is therefore the sum over X of 2 times log of 1 over Fx, and therefore is something which is larger than 0. Okay. Call log of 1 over x squared eta x, okay? And then z is the sum over x of eta x. What's the probability distribution? Eta. Well, it's just a change of variable, right? So it's the f by the eta, p of f, but p of f is just uniform there, so it's 1 over 2, okay? The f in the eta will be e to the minus eta half divided by 2. Okay? So I have to look at the probability distribution of a variable, which is the sum of independent random variables distributed with the exponential there. How do you do that? Let me take the Laplace transform. Okay? This is the product dz 1, 0 to infinity. Sorry, d eta, what's it? D eta 1, d eta, p of eta, e to the minus s eta, L times, okay? And this is 0 infinity d eta, e to the minus s plus 1 half eta divided by 2 to the L, okay? So this is 1 divided by 2s plus 1 to the L. Okay? Good. So how do we invert the Laplace transform? I invert the Laplace transform. So P of z will be the integral over the Bromwich part, ds divided by 2 pi I, e to the s z, 1 over 2s plus 1 to the L. Okay? What's the Bromwich part? Is the part that passes to the right of every singularity. The only singularity here is an L pole located at minus 1 half. So I can choose any path which is to the right of this. Okay? I can cross the path to the left and circle the pole. And since it's an L pole, we get the residue, the L minus 1 residue, divided by L minus 1 factorial. L minus 1 residue is just z to the L minus 1. And then I compute the value of the pole. There we go. Okay. Bit boring, but for the students, please do it at least once in your life, because otherwise you're never gonna do it. You're never gonna see it again. Okay. So if I go now back to the to the amplitude, taking the exponential, I find that the probability distribution of, let me call alpha AP square, okay? Just not to have a probability of something squared, you never know. P of alpha will be 1 over alpha 0 to the 3 alpha. 1 over 2 to the L alpha 0. And then we have log alpha divided by alpha 0 to the L minus 1 divided by L minus 1 factorial. What's alpha 0? It's this thing here. It's the smallest possible amplitude. Okay? The probability distribution is 0 until this alpha 0, then quickly raises up and slowly falls down, like alpha to the minus 3 alpha. Log to the L minus 1. Now, properly. Okay.
So that looks a bit like a Levy distribution.
It's a Levy distribution in some sense, because it's one of the Levy stable distributions, because
It's exactly that
yeah,
in a localized space.
yes. It's a Levy distribution it doesn't have, it goes down alpha to the minus 3 alpha. It means that it's integrable, summable, right? As you can. In fact, it was enough to check that at s equals 0 here you get 1, right? Because s equals 0 is the normalization, so you get 1. So it's normalized if I didn't do any mistake in the version. But if you try to compute the first moment, it's infinite because it decays too slow. It's a properly valid distribution, but it's long-tailed.
Yeah, with the cutoff that is given, because usually when you have
cutoff.
Yeah, exactly. Typically, when you have Levy variables, you always know that let's say out of a certain cutoff region, here the cutoff is naturally given by the school.
By the typical value.
Okay. Yeah. Okay.
This is the typical value, right? This is what you would do if you ignore complete the randomness. You will put T over W, T over W, T over W. But then there is the tails.
Yeah.
Okay. Okay. Good. We need to find the maximum. How do we find the maximum? How do we find the maximum? We should look at the distribution of the maximum. Students, do you know how to compute the distribution of maximum? You compute what's the probability that the maximum n variables max over x of certain variables, a x is less than something. So you compute the CDF, cumulative distribution function. But if the maximum of this is less than this, then all of this, all the variables are less than this. So the CDF is the product of the CDFs. So the probability that the maximum of the n variables of these variables is less than a given number m, okay, is equal to the product of the probabilities that all these variables are less than m. So the CDF, cumulative distribution function of the maximum, is the product of the cumulative distribution functions of the variable. If you want the probability distribution of the maximum, then you take the derivative with respect to the upper bound, okay? And you get the probability distribution of the maximum. This said, there is a quick and dirty way to get what's the order magnitude of the maximum. And if I extract n variables out of a probability distribution P of A, okay, of alpha, actually, it's the largest solution of the following equation. Okay? As order of magnitude works. The factors are, you know. So the typical value of the maximum is the first time that, you can imagine this, like this is like an histogram, right? So the first, I extract my 1 million objects, right? What is the maximum? Is the last histogram in which I have an extraction. Okay? So the maximum which we are after is the solution of the equation. Say, for example, if we were in d dimension, it was d to the L. Now, if we are on the Bethe lattice, we have the branching k instead of d. Okay, branching k in this case is 2. K to the L. Whatever. Okay, let's say on the Bethe lattice, we have k to the L, p to the alpha star, which depends on L, okay, equal to 1. Okay? And you need to solve this. Find the largest solution. This requires some working. The only thing that you need to beware, first of all, of course, we take the logarithm, we set the logarithm of this equal to 0. Okay. Then the other thing you need to notice is that clearly you need to scale alpha and actually log alpha with L, because this is the only way that you get an L here, and this L kills the L factorial. L to the L and kills the L factorial. Otherwise, you're not going to have anything killing factorials. Okay? So, alpha star, it's going to be alpha 0 exponential 2L zeta star, where zeta solves the equation zeta star minus log zeta star plus zeta star minus log minus log of k times e is equal to 0. Yes, alpha 0 to the L, sorry. Okay, so now you see that I've gotten a correction depending on the connectivity, dimensionality, to the typical value. Okay, good. Now,
This is also the connection.
Sorry?
Because alpha star is alpha 0 is the typical value of alpha.
Yes. And this is the correction.
And why then alpha 0 is to the power L?
Why alpha 0?
Is to the power L.
Because everything decreases with L. Alpha star is exponentially decreasing or increasing with L. Alpha depends on L. Alpha star depends on L. alpha star is the amplitude at the L, maximum amplitude over all the possible points which are at distance L, so depends on L. So if you now ask for this thing not to decrease, so okay, so and this has to be, this is e to the minus L over xi, where xi is the localization length.
Do I understand correctly that the minimum value of alpha is out to 0? Right? So this is the cutoff.
Yes, it's also the typical value, because the probability is a maximum. Alpha 0 is the minimum and very close to being the typical value. The average value does not exist. Okay, if again, this left to do as an exercise, you set xi, 1 over xi equals 0, okay? And you find the transition. The transition in terms of W, if you put everything back together, is WC is equal to 2 E K T log WC divided by 2T. And that's it. Okay. So this approximation, you have a transition with, which solves this equation here. How do we compute? How do we find the transition? We looked at all the points at a given distance. We compute within some approximation the amplitude to go to that point. We compute the maximum of the amplitude over all the points, okay? And we impose that this maximum is still exponentially decreasing. If we reduce the disorder too much, we cannot impose this anymore. When is the minimum value of the disorder at which we cannot, maximum value of the disorder at which we cannot impose this anymore? This thing here. Okay? I think this is a good moment to stop.
Yeah.
Okay.
Yeah. Okay. Yeah.
Okay.
Few more questions before we take rest, given the flu and everything. Okay, you can take rest.
Thanks.